Okay, when we first introduced 3D vectors, we talked about that a magnitude is going to be unique, and we had our 2D vectors, we had a magnitude and direction, but we moved to 3 dimensions. One direction angle isn't sufficient to uniquely define a vector. So we are going to talk today about what are called our direction angles and then direction cosines. So if we imagine a vector in space, so 3 dimensions, means I go over 3 in the x direction, over 6 in the y direction, and up 4 in the z direction. We're going to look at each axis and define a angle between that axis and the vector. So if I look at the x-axis, it looks something like that. That angle in between the x-axis and the vector we call alpha. And we also know that there's a unit vector, in this case I, along the same direction as the x-axis. And so if we can figure out the angle between those two vectors, we figured out alpha. And we can figure out the angle between two vectors with a dot product. So we're going to take the dot product of our vector and all of our unit vectors. So I dot v is the magnitude of the vectors times cosine of alpha, and the magnitude of I is 1. The magnitude of v we can figure out with our Pythagorean theorem. And then on the other side, if I think about what my components look like, well, the vector I is 1i plus 0j plus 0k. And if I take the dot product with the vector 3, 6, 4, everything is going to drop out except for the 3 times 1. So we're left with 3 over root 61, which is cosine of alpha. And we can figure out alpha with the cosine inverse from there. So we do similar thing with our other unit vectors, in that alpha is called our direction angle. So I look at, with the y-axis, we call that angle beta, and I look at the z-axis, we call that angle gamma. And beta is going to be the angle between j and our vector v, and then gamma is going to be the angle between k and our vector v. And so we just set up the same process as we did before, and we solve for beta, and then we would solve for gamma. And what's nice is that our unit vectors are going to have a magnitude of 1, and we take the dot product, since they're just zeros and ones for the unit vectors, everything is going to drop out except for the corresponding component. So and just if you haven't seen it before, that Greek letter is alpha, that's beta, and then that one is gamma. So those are unique to each axis. So we don't want to mix them up. We want to use them in order as they're defined. All right. So those are the direction angles. We're also going to talk about the direction cosines. So if we were to take another example, we just took a general case. So we know that the unit vector is going to have a magnitude of 1. If we have a general vector, ai, bj, and ck, what would happen if we go through this? Well, I dot v is a, because if I take the dot product with I as a vector is 1i, 0j, 0k, and when I multiply all the component parts, I'm going to just be left with a. And then the magnitude of v is the magnitude of v, and if I solve for cosine alpha, I get a over the magnitude of v. We also define that whole value, the cosine of alpha, as our first direction cosine. We call that one C1. We can do the same thing for beta and gamma, and what we're going to be left with is cosine of beta is b over the magnitude of the vector, and then cosine of gamma is c over the magnitude of the vector. So it might look scary, but it's really pretty easy. It's just, if we have our order triple, we find the magnitude of the vector and then take each piece of the order triple and divide by that magnitude. So we have the direction cosines C1, C2, C3 correspond with cosine alpha, cosine beta, and cosine gamma. All right, so what are we actually doing here? Well, if I look at this unit vector, if I take the direction cosines and I apply it as a vector, I get a unit vector. And that's the same thing we've done before. If I take a vector of length 10, has a magnitude of 10, and divide everything by 10, I'm going to get a value that has a length of 1. So that's called a unit vector. So we can set up a unit vector, which is going to be helpful once we get the equation of a line in vector space. So that is a unit vector. We can prove it if we look through it. I factor out the 1 over the magnitude. I'm left with a, b, and c times I, j, k. And that's vector v. So v over the magnitude of v is a unit vector as we did it before. We also have some properties about our, if we were to square these things and add them up, our direction cosines. So if we just apply what they are, that's a squared over v, the magnitude of v squared, b squared, the magnitude of v squared, and a squared plus b squared over c squared over the magnitude of v, and then I square it I'm left with 1 because the square root of something squared gives me what's back, and I get a squared plus b squared plus c squared over the same thing, which is equal to 1. So if I know two direction cosines, I can figure out the other one just by plugging it into this expression.